All right, so everything's recorded. Okay, good deal. Okay, so a quick announcement. The homework, if you have any trouble working on the homework, let me know. I can schedule one-to-one meeting with you. I did yesterday one-to-one meeting with a student. So if you miss me from office hour, you're welcome to stay a little bit late behind today, and we can address your issues. Okay, now let me circle back on the lecture a little bit. We're gonna have mainly the flasher design covered before we go into the first exam. And let me say that the first exam, I mean the first part, flasher design, is very critical for the whole entire RC concrete design. This course is very fast paced. I strongly suggest you hang in there, just keep up with the pace for the first period. And once you get over the hump, the next part will be relatively easier, okay? Relatively easier. So first of all, you guys be able to see my screen here? You guys be able to see my screen?
Yes.
All right, good deal. So let me recall a little bit what we learned from last lecture. We talked about the Whitney stress block, okay? And this Whitney stress block generated from this issue that we have a problem. We have a problem in terms of the stress distribution in concrete beams, okay? Since we have that linear distribution of stress, we cannot easily calculate the moment resistance that way. So instead, we use the assumption which assumes that the stress distribution is a block. It's a block, okay? And we also assume that width of the block is 0.85 F prime C. The height of the block is called beta 1 C, where beta 1 is a reduction factor on the actual compressive zone C, where A is beta 1C, the product, beta 1C is the effective compression. Okay? And also, in this setting, we always assume that epsilon S is bigger than epsilon Y, okay? Which means the stress in the steel equal to the yield stress, Then we further separate the internal forces into compression force by concrete, CC, and tension force by the steel, T, and the concrete is sitting at 1/2 of A, away from the top fiber. We call this top fiber right here on the top, okay? We call this top fiber, okay? And then the tension is sitting at D minus half A away, JD away from CC, okay? So that's the general setting for the Whitney stress block assumption, right? So with that, we come up with the equation compression force 0.85 prime CBA, CC equal to tension force T, T equal to ASFY, where AS is reinforcing area, and then we can compute A using this equation, all right? Once you compute A, you go back to C, and once you have C, you can find the strain in the steel, and to make sure that the strain in the steel is bigger than the yield strain, okay? So this is very critical, okay? Always go back to confirm that the steel strain in the steel is bigger than the yield strain, okay? Then we have the moment. Any question? Question? Are we good? Are we good? Okay, so I'm gonna go on. So once we have the moment, okay, and we are going to calculate the stress reduction factor later, okay? But to give you an example how it works, okay? First of all, let's talk about beta 1. So beta 1 is a coefficient that solely depends on the concrete strength, okay? So if it's a 4 KSI or below, it's 0.85. If it's 8 KSI beyond, 0.65. And there's a typo here, okay? I believe the note I posted is correct, but there's a typo here. There should be 8 KSI, okay? There should be 8 KSI, okay? Sorry about that. And then once we have beta 1, we can go back and find the C and follow the process to compute the moment, okay? Follow the process, compute the moment. Okay? All right, so that is the general process to compute the nominal moment strength for a singular reinforced beam, So I have an example here I didn't go through last time. So let me quickly go through this, okay? So I have a beam, that rectangular shape, and then it has a width of 12 inch, height of 20 inch, I have 4 number 8 bars at the bottom, Have a couple. Yes. Look. Any question? All right, okay. So let me carry on. So we have a concrete cover 2.5 inch, and then the concrete strength is 4 KSI. All right, and the yield strength is 60 KSI, grade 60. Okay. The question is, what is the nominal moment strength Mn here? All right. And to find that, first we draw the Whitney stress block. Okay, this is what it looks like. 0.85 F prime C and has effective compressive zone A and have a tension force ASFYT. Okay, so to solve the problem, this is the procedure. Okay, this is the procedure. You first calculate the reinforcing area AS by number of bars. So there are 4 bars. Each bar have an area of 0.79 inch squared. This is for number 8, and have a total area of 3.16 inch squared. Okay, now the tension force T equal to ASFY because the section supposedly yielded. So what I'm trying to say is whenever we solve the problem, we automatically assume it's yielded. Okay, assume it's yielded first. Okay, then 3.16 inches squared multiplied 60 KSI, that gives me 190 kips in terms of the total tension force, Okay, so with that, okay, I can carry on to find my effective compressive zone. Carry on to calculate my effective compressive zone, which is A, and that is beta 1C, and then equal to ASFY, tension force on top, 0.85 F prime CB, which is the bottom here, okay? And then I got 4.66 inches, okay? Now this 4.66 inches is the effective compressive zone, okay? Effective compressive zone, okay? This is not C yet. So we still need to find C, which is the actual compressive zone, check if it's yielding. So we use C equal to A divided by beta 1, and that is 4.66 right here, divided by 0.85 because of 4 KSI, and I got 5.48 inch of the actual compressive zone C. Okay? With that, I'm going to check my strain. So the strain epsilon Y equal to Fy divided by Es, okay, that's the yield strain, and equal to 0.00207. And you guys already know we need to remember this number, okay? We need to remember this number, okay? It's 0.00207, okay? And once we have that, I can compute the strain in the steel, which is epsilon S equal to D, which is depth minus C divided by C, multiplied by the concrete failure strain, epsilon Cu, which is 0.003. And I got a final number of 0.00658, which is bigger than the yield strain, hence okay. It's okay. Okay. So the whole idea is to verify that it is yielded. It is yielded. Okay. Once I have that verification, I bring the equation back here, use my nominal moment strength equation Mn equal to tension force ASFY multiplied by distance D minus half A, and I bring the number in, I got a total moment resistance 2,880 kips inch, okay, kips inch. And I convert that into kips feet by divided by 12, I get 240 kip feet, and I'm okay. All right. So at this stage, I got my nominal moment strength. I should be happy. I should be happy. There's one thing I haven't talked about is there's actually a lowest, a minimum requirement on a reinforcement. Requirement on a reinforcement area, ASM. Okay. So here we go. First question of today. Okay. Why do we need a minimum reinforcement for the concrete beams? Okay. So let me ask this first before we get to that. If I have a concrete beam, okay, if I have a concrete beam, okay, and I'm lifting it in the field, okay, for example, I have a beam, I'm just having a hand in the middle, just pull it up, right, like a crane, lift it up, okay, and if there's no reinforcement in it, okay, if there's no reinforcement in it, if I try to lift the concrete beam, what would happen? What would happen? Mike?
Would the beam just break and fall?
Yeah, why the beam would break, you think?
Because the beam itself can't handle the tensile stress that the rope will enforce onto the slab.
That's very good. That's the good point, right? So there's a self-weight of the beam, first of all, right? So when you're trying to lift the concrete beam out, the beam is actually bended due to the self-weight. However, though, the strength, tensile strength for the concrete is very low, so it can easily break down. Okay, so there's an instance in aircraft hangar structures back then in the military base where they forgot to put enough reinforcement in it. They just use some mesh wire. So they did a calculation. They suppose that the self weight would not crack the concrete, but end up fitting the beam. Hence then, the ACI published a minimum requirement. That means whatever loading you have, even if you don't have any load applied to the beam or just self weight, you need to put this much reinforcement, okay? And this is a criteria. So the criteria is the minimum required reinforcement for flexure is a larger number of these two. Larger number of these two. What are these two? First is 3 square root of F prime C in PSI divided by Fy, which is yield strength steel, multiplied by B is the width of the section, and D, which is the depth of section, okay? Or 200 divided by Fy, B multiplied by D. So the bigger of these two. In our case, the second term, 200 divided by Fy, B, D governs, means this is larger requirement, okay? So we calculated that and said 0.7 inch square is the minimum requirement on the reinforcement area, okay? You can find this from ACI code 9.6.1.2, okay? So we have to do one more check before we let go. So the provided reinforcement area is 3.16 inches square, which is bigger than this value, okay? So we're okay, okay? So that is just a general procedure, how you do analysis for a singularly reinforced beam, okay? So I'm gonna close share and start talking about our second part of the lecture, okay? Second part of the lecture. Before I stop there, let me try to ask a question here. So for singularly reinforced beam, right? For singularly reinforced beam, I just have one row of reinforcement, okay? And I can have the beam yielded. All right, that means the steel will go to this plastic stage or go through a permanent strength Fy and keep elongating, okay? So quick question here, okay? And I'm gonna name my next victim, Bryce.
Hey.
How are you?
Good. How are you doing?
So good. Well, fortunately, you're the next victim, okay? So question goes is, do you think when we design the reinforced concrete beam, okay, do you think we prefer the steel to yield or we prefer the steel does not yield?
Probably not to yield,
Why?
because once it reaches past that point, the concrete, it kind of deforms. So
Okay.
maybe, yeah.
Yeah, that sounds good. But let me turn around this way. Yes, we don't want to fail, right? We want to be safe, right? Say if we keep loading it, and the beam inevitably have to fail, okay? And during the failure, do we want to see a brittle failure or we want to see a ductile failure?
Probably a ductile.
Okay, so in that scenario, we then want the steel to yield, isn't it?
Mm-hmm. Yes.
Okay, good point, okay? So from the loading point of view, we don't want to increase our loading to let the steel yield, but from a preferable failure mode's point of view, we want the steel to yield, so we have more time to run, right? We have more time to run, right?
Yep.
So that's the good answer, okay? So given that thoughts, okay, let's take a look at some critical concept here, okay? So let me share my board with you. Okay, so this is lecture 2. Okay, lecture 2, concrete. Okay, so today we're going to talk about some critical concept. Okay, some critical concept. Now, as I said, right, we want the beam to fail. Okay, so there's a state that beam in. So today we're going to talk about the balance condition. Okay, balance condition. New word of the day, balance condition, okay? The beam has to be in balance, okay? And also there's another concept, it's called strength reduction factor concept. Strength reduction factor, okay? And together we'll talk about multi-layer reinforcement. More than one row of steel at the bottom, okay? More than one row of steel at the bottom, okay? So the course objective for this, we have objective 1. Of course, we need to learn balance condition. Okay, and we need to learn the stress reduction factor, right? For example, we need to understand the concept of that. Now the second objective is we need to analyze a multi-layer reinforced beams. Okay, so these are the 2 objectives for this class today. Okay, so let me talk about the first one. So 2.1, okay, balance condition. Okay, what is this balance condition? Okay, and then how do we determine if it is a balance condition? So this is determined based on the strain in steel. This is determined based on the strain in the steel. Okay, so let me show you some of the figures. Okay, some of the figures. So I have a beam. All right, let's assume I have only one row of reinforcement to start with, and I call this AS, the reinforced area. I have a width of B, okay, height of H, depth is D. Okay, and then I'm plotting the strain distribution diagram. All right, so of course it always looks like a triangle, right? Always look like a triangle. So my next quick question here, Austin Horskamp, Mr. Horskamp.
Yeah, hello. Yep, I'm here.
Oh, yeah, I can hear you. Can you hear me?
Yep.
Okay, so quick question here. What is the compressive strain in concrete when it fails, when the beam fails? What is the value for epsilon Cu?
29,000.
Oh, that's the Young's modulus still.
Oh, that means
Start from 0.0027.
27.
That's a yield strain. One more chance. That's okay. 0.00. Concrete is.
Yeah, sure. 3.
Yeah, pretty close. Okay. So remember this number. Okay.
Well, I rounded up.
What's that?
I said I rounded up.
You want? Yeah, sure, of course. But be careful. Okay, that's 0.027. Okay. One more digit. Okay. A good answer. Okay. Keep remember that. That's the failure strain for concrete. It does not change. Okay. All right. So it does not change, and we say this is neutral axis right here. Okay. And I have my steel right here, and we reach a strain from the steel epsilon S. Epsilon S. Okay. So this is my compressor zone C. And then I call it balance condition is when the strain in the steel epsilon S equal to the yield strain epsilon Y. Okay, so in this condition, beam is balanced. Right on the balance point, okay? And I can actually calculate the compressive zone at balance, use this triangle here, and that equal to a D depth divided by epsilon Cu plus epsilon Y, okay? And then the balance compressive zone equal to epsilon Cu divided by epsilon Cu plus epsilon Y, okay? And then this is D. And let's assume that epsilon Y equal to 0.00207, okay? That's the yield strain. And my next victim, Lucas.
Yeah.
You there?
Yeah.
All right, so quick question. So the yield strain epsilon Y equal to 0.00207, that's for what grade? Grade 70, grade 60, grade 75, which one?
Grade 60.
Great, that's the correct answer, grade 60, thanks. Okay, so that's grade 60. Assume it's a grade 60, so I got a balanced compressive zone divided by the depth ratio closely equal to about 0.003 divided by 0.005, and I got approximately equal to 60%, 0.6, okay? So that means if I reach the balance stage, my actual compressor is only about 60% of the depth. 60% of the depth. So this is called a balanced condition. This is called a balanced condition. Okay. So I'm going to mark this shape, and I'm going to put here and zoom in to show you something, right? So this is the strain distribution, okay? So at a balance point, epsilon Cu is equal to 0.003. So imagine, okay? Of course, I cannot increase the failure strength for concrete. I cannot do that, but I can keep bending my beam. Bending my beam, right? So if this is the balance point, okay, I have two possible scenarios. One is I can bend my beam this way so that I have less tension and more compressive zone. Okay, so if this is epsilon y, and this epsilon s here is smaller than epsilon y, isn't it? Smaller than epsilon y. So this case, is it still yielded or not? Is it still yielded or not? Abraham.
Yes, doctor.
Hey, good morning. Good to see you.
Hey,
So far away from.
thank you.
All
Yeah.
right. So quickly, the question is, if I have the red scenario, the strain is still smaller than the yield strain. Is it still yielded or not?
Well, I just joined up, so I didn't know. I haven't heard the first thing what you were explaining.
No worries. Let's do a pick. Yes or
Yeah.
no? 50% chance of winning here. Yes or no? Yielded or not?
Yes.
Yielded? Okay. You got. I'm like. All right. But
Did I get it right?
that's okay. That's okay, right? So this case, we do better next time, right? We do better next time. This case, not yielded. Okay. Not yielded.
Okay.
All right, thanks, Abraham. So in this case, it's not yielded. So we call this, okay, very important. We call this over reinforced. Means too much reinforcement. Over reinforced. Okay. So when you have a strain still that less than the yielding strain, that's called over reinforced. But I have the other possible scenario. Okay. Possible scenario. I use a purple line here. And I have this scenario where my epsilon s is bigger than epsilon y. Okay, and this is called under reinforced. Under reinforced. Okay, and naturally in our design we prefer this. Okay. Okay. So the balance condition, okay, the balance condition is very critical, okay? We need to figure out a balance condition and then we decide what type of failure mode we'll have. Is this yielded or not yielded, is over reinforced or under reinforced, okay? So that's how we define it, Hence, if we have this under reinforced and over reinforced case, I can summarize it, right? I can summarize it. So actually in ACI, there's a tiny table. Okay, tiny table. That provides a reference number later. And then depends on the condition, right? Depends on the condition. I divide the strain, divided by the strain by 3 different categories. So if the category epsilon in the steel, I call it epsilon T, okay? And I'll explain what is epsilon T, okay? If epsilon T is smaller than 0.002, okay? If it's smaller than 0.02, it's over reinforced. Okay, and the strength reduction factor phi is actually 0.65. Okay, 0.65. And if epsilon T, okay, the strain in the steel is between 0.002 and 0.005, is in between, and I call it what? Transition, okay? And phi has an equation as variable epsilon T, which we'll talk about it, okay? Transition when I have epsilon t bigger than or equal than 0.005, I call it under reinforced. Okay, reinforced. Okay, so these are the division of our design failure mode. Okay, design. Okay, for design. All right. So you see that with different strain in the steel, I have different strength reduction factor phi. Okay, different strength reduction factor phi. So what it is, right? What it is, the strength reduction factor phi. Okay. So first of all, well, let me write this down. We're going to talk about 2.2 strength reduction factor. What is the strength reduction factor? Okay. Okay. So the strength reduction factor, recall, we mentioned before, use it to reduce the nominal strength mm and allow it to be bigger or equal than the applied moment u. Okay, and then you notice that there is the epsilon t instead of epsilon s, right? What's the difference? So first of all, let me draw a section here. And let's say you have two rows of rebar, okay? One row like here on top, the other row a little bit lower down here, okay? Two rows, okay? Naturally, these two rows will have a geometric center here in a triangle, okay? So by definition, the distance between the top fiber, which is this top fiber, we call it top fiber, okay? Top fiber to the center of the group of the bars, we call it D. Okay, this is D. Okay, so naturally, if it's one row, then we just have D equal to the last bar, right? Last row. Okay, but we call the last row. This is the last row. Okay, last row of bars. Okay, last row of bars. Okay, and the distance. Sorry, slipped on me. The distance is actually dt. Okay, that's where the t coming from. And then the strain at this level is epsilon t. So that means my strength reduction factor was determined by the strain in the last row of reinforcement. Last row of reinforcement. Okay, so pay attention, right? So that is the cross section. That is the cross section. So I'm just gonna put it here. Okay, on the side. Okay, so that is definition of the epsilon t. And then looking back on this strength reduction factor phi, okay, I'm just trying to plot the equation here, okay? What it looks like is actually like this. So now I know the phi, strength reduction factor, is a factor of the last row strain epsilon t. I can draw the curve, okay? And I can pretty much define if it's 0.002 or below, my phi is actually lower. 0.65. Okay, now if that is 0.005 or bigger, my phi is, number here is 0.9. 0.9. Now in between, I directly connect the dots and make a linear line. Sorry, didn't miss a line, but make a linear line. Okay, this is the transition. So this is transition. Under, over. Okay, three different zones. And I have equation for them. So the equation for phi, stress reduction factor, equal to this below. Okay, so this is a 0.9. Okay, when epsilon t is bigger or equal than 0.05. Okay, and then 0.65 plus 0.65 plus epsilon t minus 0.002 multiplied by 250 divided by 3. Okay, and this is when epsilon t is smaller than 0.005, but bigger or equal, well, not equal sign, but bigger than 0.002. Okay, and then if it's smaller than 0.002, it's 6.65. Okay. Okay, so that is the stress reduction factor, and you can find this from ACI code 9.3. Okay, 9.3. Okay, so that means based on the strain level of strain in the steel, I will have a different design factor. Okay, so you can take a look. If I have a larger strain in steel, I have a bigger stress reduction factor. When I have a smaller strain in steel, I have a smaller stress reduction factor. Okay, so what it means is if I have a yield in the beam, I have more safety in it. So I assign a higher number of stress reduction factor. When I have no yield in the beam, I have more concern in the safety of it. So I reduce less. So it means I use I reduce more. I use a smaller number of stress reduction factor. Okay, so that means we prefer yielding. We prefer yielding. Okay, all right. So now take a look. So currently we have gone over the balance condition, how to determine the stress reduction factor, and we're ready to solve problems. We're ready to solve problems. Okay, so let's take a look at the problem. Okay, let's take a look at the problem first. Okay, so right here, go to example number 3 here. So 2.3. Okay, example, right? I'm going to use this to solve a problem. Okay, and nevertheless, last lecture we used 1-layer reinforcement. Okay, I want to show us how to do 2-layer reinforcement. Okay, so multiple layers of reinforcement. Okay, multiple layer reinforcement. Okay, so I have a beam. Okay, and now I say I have 2 rows of reinforcement. Top row, I have 2 number 9 bars. Okay, bottom row, I have 4 number 9 bars. Okay, bottom row, I have 4 number 9 bars. Okay, and then the height of the beam is 20 inches. Okay, and I'm going to go ahead and give you the width of the beam, 12 inches. And to save your time, I already pre-calculated the center for the group of bars. Okay, I already pre-calculated the center for the group of bars. And that sets me at D equal to A, 16.8 inches. Okay, and we'll talk about this in the Thursday review session, how you calculate that in detail, okay? In detail, okay? And also, I have my last row of bars, naturally here.
You writing the example.
Can you guys see my screen?
We can see it, but we can't see what you just wrote down.
Oh, okay. Let me stop sharing and you can see again, okay? Let me try this again. Can you see the update now? Is it better now? Okay, sorry about that, okay? Some glitch in the software, okay? So quickly recall in case we forgot anything. So this is the configuration. I have 2 number 9 bars in the top row, 4 number 9 bars in the bottom row, and I pre-calculate the center of the group of bars, and that sets us a D equal to 16.8 inches, and DT, which is the last layer bar, equal to 17.5 inch, okay? That's good. It's good. Now the concrete is really normal concrete for KSI, okay? And I'm gonna use grade 60. I'm using grade 60, okay? All right, so number 9 bars, right? Number 9 bars. So happen to be the area AS, right? For number 9 bars. Per each bar is 1 inch squared, okay? 1 inch squared. That's why it is my favorite bar, okay? What I'm trying to tell you is if you see a number 9 bars, you are in luck because each bar have a cross-section area of 1 inch squared, okay? 1 inch squared, okay? So that is our problem, right? Let's try to solve it together, okay? Let's try to solve it together. So solve first step. Now I don't know anything about the cross section, right? I look at the cross section, I'm gonna say, I assume still yielded. No reason, right? Every time, it's still gonna yield, okay? So assume still yielded, and then I can proceed to compute the actual compressive zone A, okay? And I can get my, effective compressive zone A first, and get my actual compressive zone C, and then get my strain in the steel epsilon S, okay? I purposely put here epsilon S to differentiate from epsilon T, okay? Different epsilon T, okay? All right, and this is all under assumption that assume yield, okay? Assume yield, okay? So now I can start my calculation, right? So A, which is the effective compressive zone, equal to beta1C, and equal to ASFY divided by 0.85 F prime CB using the Whitney stress block, using the Whitney stress block. And that gives me a 6 inches squared. Where's that 6 coming from? 6 bars, right? 6 bars, right? And each bar have 1 inch square. So AS equal to 6 multiplied by 1 inch squared, so equal to 6 inch squared, right? 6 inch squared of reinforcement multiplied by 60 KSI of strength, 60 KSI of strength, divided by 0.85, okay? And 4 KSI, and the width is 12 inch. Width is 12 inch, okay? And then I get a number of 8.82 inches. And that's the effective compressive zone, okay? To get the strain in the bar, I cannot use the effective zone, right? I have to use the actual zone. So the C equal to A divided by beta 1. So equal to a 10.4 inch. 10.4 inch. And keep in mind that beta 1 equal to 0.85 for F prime C equal to 4 KSI, okay? So this is embedded already, okay? So naturally right now, I'm gonna use my epsilon S to say the judge is still yielded or not. Okay? So I'm gonna use the D minus C divided by C, okay? Multiplied by epsilon CU, all right? So now, which depth should I use? Okay, question here, which depth should I use? Jack? Meadows? Jack?
Yep, I'm here.
Hey, how are you, man?
Good.
Good. So quick question here. I'm trying to calculate my strain steel, right?
Yeah.
Notice that's epsilon S here, okay? Which depth should I use? Should I use D or should I use DT?
D.
Okay, good one, right? We should use D always, right? So that is the lower number, 16.8, okay, minus 10. Well, thanks, Jack. Good answer. Okay? And divided by 10.4, okay? And multiplied by 0.003. All right, so I forgot to do my homework on this one, so I need somebody to help me out with the number. So I'm gonna pick our next victim, who's gonna be Adam. So on my screen, can I get a help on this quick calculation here? Can you see my screen?
Yes.
16.8 minus 10.4 divided by 10.4 bracket and multiply 0.003.
I'll get that going.
Yeah, all right. Okay. And while Adam's getting going, and we're just trying to compare this with the yield strain. What's the number?
0.0018.
1.8.
Or I guess 185.
Oh, that's good. Thanks.
2 decimal.
Yeah. So for our strain calculation, we need 1, 2, 3 digits. Okay, at least 3 digits. Okay, this is for you guys. Okay, 3 digits at least. Okay, effective. And this is smaller for sure, smaller than the yield strain, right? It's 0.0207. Okay, not good. Not good. Okay, so it means the steel does not yield. Does not yield. So what to do? What to do? Now, if we were in a design session, we will just replace our reinforcement to make it yield, However, we were given the section. And the section is locked. We're here just to do the analysis, okay? So there's no way for us to redesign it, okay? So we just have to use whatever we have, all right? So we finished the first step and knowing that does not yield. Can we use the equation to get the moment strength still? I mean, can I use this ASFY, D minus half A, and proceed and blah, 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 blah. Can I do that? Can I do that? Marshall. Hello. Hey, Marshall. So here's a quick question. I know that my steel does not yield. My steel did not yield. Can I use this equation to get my moment strengths? Can I use this equation to get the strengths, nominal flexure strengths? Did I drop you, Marshall? Oops.
I'm not sure on that one.
Mm-hmm.
I still don't understand why you want it to yield either.
Okay, so if we have a beam and the steel yielded, and yielding steel means the steel will go into a permanent deformation with a holding strength, right? That means your structure will graciously deform, right? So it takes a longer time for the ultimate failure to happen, so you have time to run, okay? Now, if you does not allow the steel yield, it's gonna be a brittle failure where concrete crushes. Where the concrete crushes, it loses strength immediately, so there's nowhere for you to run. It just fell on the side instantly. Did you get it?
Yeah, I understand that.
So every time we prefer the steel yield, okay? So now, mathematical question right now is that if the steel does not yield, can we use the old equation to calculate the moment?
No.
No, that's a good question. Good answer, okay? So the question is no, cannot use it. Thanks, Marshall. So the problem is, why can we use it? Why we cannot use it, right? The problem is we don't know A anymore. We don't know A anymore, okay? Why? Because we don't know whether the steel, right? We don't even know. This is not Fy anymore, isn't it? We don't know the tension force anymore, isn't it? So we have to go back to the drawing board, in this case, to find out what actually stress steel is seeing, okay? What actually the stress steel is seeing, okay? So in that scenario, let me go back, okay? Since this is not working, I'm just gonna put a big mark on it. So this is not working. So it does not apply. Okay, so I'm going to use the old equation to figure out, right? So now I know tension equal to AS F instead of Y S. Okay, I don't know if it's going to yield or not. Okay, this is not yielding, so I don't know the strength, right? I don't know the stress. So I'm going to write it out as AS ES modulus elasticity for the steel multiplied by epsilon S. Okay, epsilon S, which is the strength. And I'm going to use AS multiplied by ES, okay? And here, D minus C divided by C epsilon C. Okay, that means the tension force now is dependent on the compressive zone side C. So if I know C, I can get the tension force. Okay, now let me take a look. So now the strain distribution looks like this. So here's epsilon Cu, and here's epsilon S. I don't know the number of that, but there's something lower than the U strain, okay? So this is C, that's the actual compressive zone, and I have a depth here, D. Okay, so I don't know what kind of compressive zone I have, right? But I do know one thing, that tension has to equal to compression in concrete. That means it has to equal to 0.85 F prime C. B beta 1 C. Okay, So today, and now we're going to talk about a very important concept in reinforced concrete design is iteration. Means guess, right? Guess. So in this case, I have to try. So let me try compressor zone C equal to 10.1 inches. Okay, it's just my guess. Okay, so if I try that value, I calculate my tension force equal to AS, ES, D, which is 16.8 minus 10.1 inch divided by 10.1 inch multiplied by 0.003, okay, which is epsilon Cu, okay? And don't forget T, this equals 6 inch squared multiplied by 29,000 KSI, okay? And this whole thing, 16.8 inch minus 10.1 inch divided by 10.1 inch and multiplied by 0.003, okay? And I got this number equal to a 3, 4, 6 kips. Okay, and I checked my compression force from the concrete equal to 0.85 for KSI and B 12 inch and 0.85 strength reduction factor, and also the compression zone, which I assume is 10.1 inch. And I got this number to be CC equal to a 350 kips. Okay, so now I will observe T is approximately equal to CC, right? Tension approximately equal to compression. You see, they're not exactly the same. How do you say they're the same? 5% difference. Okay, very small, 5% difference. So I think they're approximately equal, okay? Approximately equal, okay? Which means I got lucky, okay? So now I have determined, so let me finish the loop. I'm saying determined, right? So C compressive zone determined. So if you don't get this equal, right? You got to keep trying. If not, try different. C, okay? That's the iteration process. Okay? We have more details in tomorrow, Thursday, in the meeting review, okay? Try different C, okay? So through this iteration process, okay, I can determine my actual compressive zone C and get my moment, right? So once I determine that, I just got lucky, right? I got lucky. I got my number. So I can get my A, right? I can get my A. So A equal to beta 1, C equal to 0.85 multiplied by 10.1 inch. And I have this number to be A 0.85, 10.1 inch. I get a little bit help here, so it should be 8.5, so 8.9.3 inch, roughly. Okay. And then I can calculate my moments. So Mn now equal to tension. Notice I did not use ASFY, okay? I just use tension and D minus halfway. It's halfway. So tension now equal to 346 kips. I just calculated. And D 16.8 minus 9.3 divided by 2. And I got a number of 4,350 kips inch. Okay, and that equal to a 363 feet. Okay, so in a case where your strain of steel does not yield, or strain of steel is smaller than the strain for yielding, then you have to recompute the compressive zone C and get your tension force that way and finally get your moment this way. Okay. Okay. So once I have moment, the next step is to compute the strength reduction factor. Okay, compute strength reduction factor. Phi here. Okay, how do we do that? Based on the strain, right? So we said it based on epsilon T, which is the strain in the last row of steel, right? Strain in the last row of steel, okay? So very simple equation here. We use the T minus C, which is the compressive zone, divided by C, and multiplied by epsilon Cu. Okay, and then D, we already got it, 17.5 inch minus C, which is calculated 10.1, well, we guessed it, 10.1 divided by 10.1 here, and 0.003. Okay, turn out epsilon t equal to 0.0022. Okay, 22, all right? So phi will equal to a 0.65 and plus 0.0022 minus 0.002 multiplied by 253. And why is that? Why we use this equation? Because epsilon t is between 0.2 and 0.05, 0.002, so transition. Okay. Transition. So we use this equation. And then we'll get this number to be a 0.67, 67%. So you multiply phi in front of mn, and I got a 0.67 multiply 363, and I have 243 cubic feet. That is the moment capacity I have for the beam. Okay. So that is the moment capacity I have for the beam. Okay. All right. So any questions on this? Are we clear on the process, how we got here? Any questions? I'm running out of time, so any quick questions? All right. You guys are probably digesting, okay? So I already uploaded the notes. You can see it on campus. So take a look at that. We'll talk about this Thursday, tomorrow, okay? In a review session, we'll talk in details about this, okay? I get more questions and problems for us to practice as well, okay? For us to practice as well, okay? All right, so my time is up. Whoever have questions, welcome to stay behind so we can discuss. If you have any other question regarding the lecture today, that's okay too. So I'll talk to you, okay? If not, I'll see you tomorrow, all right? Thanks a lot.